So I'm excited to talk today a little bit about Databricks, what we're building at the company, which is, we believe is a new kind of data platform, and it combines a lot of elements of sort of traditional database engineering, but also quite a few things to deal with modern workloads. So I want to start by saying this is a really exciting time to work in data because the times are changing, and it means users kind of need new platforms. And I think the times are changing in several interesting ways. First of all, enterprises, of all sizes are starting to adopt large scale data. By large scale, I mean in the scale of petabytes and beyond. It's so easy now in many industries to collect fine-grained data, either about the physical world or about users doing things on a website or inventory in a store or stuff like that. And so all businesses are starting to collect this and analyze it. So that's one change. It's not limited to just large web companies anymore. Second one is that all enterprises are using machine learning. Virtually every company we talk with already has a machine learning team. They already have a few projects, and they want to do many more projects with machine learning. So it's no longer a thing where you say, well, first they got to hire someone to do it. Now, everyone is already using that. So you can actually start building software to make it much more powerful. And then finally, of course, computing is moving to the cloud, and that also gives us a chance to redesign data systems. So this is just a great time to look at data systems in general. Now, what are we doing in this space, and what's kind of our experience been? So Databricks is a startup founded in 2013, and we're a cloud-based data and machine learning platform that runs on top of the public clouds like Amazon and Azure and Google Cloud. And we've grown quite a bit since 2013. We have over 5,000 customers now, and we run large-scale workloads. So in total, we're running more than 10 million VMs per day across these public clouds that are processing exabytes of data per day. It's actually a larger scale than a lot of the cloud providers' own data analytics services. So we're definitely learning a lot about what it takes to operate at that scale. And we also have exabytes of data under management across our customers. Our engineering team is up to about 800 engineers now. We've been growing quickly, and we're still growing in that area. And the use cases are pretty diverse because we're seeking, to make a platform that actually lets different users in an enterprise collaborate. So they go all the way from extract, transform, and load to data science, machine learning, and recently in the past 2 years, we've started to do data warehousing as well. This is something we weren't doing much of before. Just to give you a sense of what is it actually? What do I mean by a platform? It's all software that we build. So we have users. As I said, there are different kinds of users. We target from data scientists to business users, and we provide services that we're running. It's a bunch of machines that we're running in the cloud to give you things like interactive data science workspace with notebooks or SQL endpoints for connecting your SQL tools, or job scheduler, machine learning platform features, stuff like that. And then, all of these end up running compute, and we run compute clusters, and we access cloud storage like S3 and Azure Data Lake Storage and so on. And these are both actually usually in the customer's own cloud account. So if you already have a license agreement with a cloud vendor and a discount and so on, you can just use it. We'll just run machines in there and use your existing storage and launch VMs and so on. And the whole platform is also built around open source projects and open APIs. So we started out as the Apache Spark team from UC Berkeley. So we run an engine based on Spark. We've modified it quite a bit since we started the company for pretty much all our computing. We also launched Delta Lake, a data management project that I'll talk about, MLflow, widely used machine learning platform project. And we also integrate with other open source tools that people run on the platform. So one of the key things, though, that I want to highlight is we're really trying to get all these users, not just to each be happy on their own, but to be able to collaborate seamlessly, because that's where a lot of the friction is in data workflows today. So I'll talk more about that later. Now, what kind of things do people do with the platform? So here are just a few examples to give you a sense. And as you can see, they're in very different industries. So Shell is an industrial company. They have to figure out how to produce things in all their plants that are processing chemicals, where to store things, when to order new things, and so on. And all of these plants are heavily instrumented, so you can get fine-grained data from every machine in there. And so they're using everything from machine learning to just business intelligence, business users clicking around in Power BI and Tableau on petabyte scale data to optimize their processes. HSBC is a bank that has over 170 petabytes of data that they're working on with Databricks. This used to be in 14 different databases in different places, and now they have a single platform to work across all of it. And Regeneron is obviously a biotech company, and in biotech, there's a huge effort to take detailed genomic data and combine it with medical records and actually develop new drugs based on that. So there are new drugs that they've developed using our platform. This is a plot here showing how the platform is growing day by day. This shows the number of VMs we're running per day. And as you can see, it's increasing quite rapidly still. It might look like back in 2018, we weren't doing anything, but actually, we were a company with like tens of millions of dollars in annual revenue and so on, even back then. But one of the things with modern data workloads and with cloud services in particular is the data volume keeps growing. Once someone sets up, a pipeline in production, they go on and develop new ones. And so there's a lot of room for growth as enterprises basically, figure out how to use these new tools and start building more and more applications with them. So we also have to scale along with that growth. And what's unique about us that maybe we can tell you that others won't do. So first of all, we're one of the pioneers of a new system architecture that we're calling the Lakehouse that aims to combine the best features of data lakes and traditional data warehouses. So we're taking this different approach. We're not going out and saying, oh, we're just a data warehouse. We're actually trying to give people a new kind of platform to think about. We built everything for the cloud from the beginning, and we designed, so for example, our version of Spark, our compute engine is designed to be elastic and obviously to be operable at very large scale. And we also have a diverse range of users, as I talked about, so we can kind of see all the interactions and challenges across them and try to design platforms that improve that. So in this talk, I'm going to cover 4 things. I'm going to talk about, hey, what is this new system architecture, and give you a little bit of insight into what problems enterprise users have that motivate this. Then I'm going to talk about how we're building our system, some of the technical things. I'll also talk a little bit about what it takes to run a large-scale cloud service. I actually have a different sort of detailed talk on that I can point to as well, but it's very interesting. And basically, this is one of the things that I'm worried, right now, no one gets to learn in universities, for example, and most software today is delivered in the cloud. So it's important to really figure out what's different here. And then I'll talk a little bit about ongoing projects with me. Okay, so Lakehouse Systems, what are they and what now? So to understand, why we're going out with this kind of new platform name and design, it starts by looking at what matters to users of data platforms in an enterprise. So if you think of, the typical user sitting and using your database or whatever system you build, you might think that, they care about things like performance, functionality, whatever, like do you have all the built-in functions and types? And they do, but these are actually often not the main problem that data users have. The top problem, if you talk to them, often have to do with the data itself. So their experience using your, whatever you build, data warehouse, graph database, whatever, is going to be really bad if the data they get in there is not great. So first problem is just access. Can I even get the data I want in the platform I'm using? If it's not, in the tools that I use, then I can't use them. And that's a big problem with a lot of tools. The second one is reliability. Okay, there's some pipeline that puts the data into my tool, but is the data correct? Does it have all the fields I want? Is it processed the right way? Again, if it's incorrect, you can't do analysis regardless of how fast your data warehouse is. And then the third one is timeliness or freshness. If the data is 2 months old and you're trying to figure out a problem today, it's not gonna work. So without great data, you can't really do any analysis. Just as an example, Fivetran ran this survey of data analysts a couple of years ago, and basically they show these issues. So 60% of them reported data quality as their top #1 challenge. They can't do business analytics without quality data. 86% of them had to use stale data, and 40% said it's more than 2 months old because of the way their enterprise moves data into the systems they use. And then 90% had unreliable data sources. Okay, so now looking at this, you might say, well, quality, making data high quality is hard, making it timely is hard. So, is this actually solvable? And it definitely is an intrinsically hard problem. You have to, you have to work on it. But one thing I want to point out is that it is also a problem with the system architectures that people have today for working with data in a company. And that's the thing that we can fix as system designers. So let's talk about how those architectures evolve. So today's analytic systems started out of data warehouses, which were and still are highly successful system design that began in the 1980s. And the idea in data warehouses was you will design a database that's optimized for analytics. And you'll take your operational systems that are processing transactions and you'll ETL data out of all of those into this one data warehouse. Then on top of that, you'll transform the data to a schema that's actually suitable for analysis. And you'll have all these features that make it easy to do analysis. So things like schemas, indexes, transactions, and so on, both performance features and management features that allow a lot of people to work and experiment with new workflows, derive new data sets. And so that was the idea. So it worked, extremely well. It makes a lot of sense to have this kind of system optimized for historical data. But in the past decade or two, there've been a bunch of new problems for these data warehouses. So one of the problems was that they couldn't easily support unstructured and semi-structured data, which was growing very quickly. So things like time series, logs, images, text documents, and so on. So they, because these were designed for tables with small records from business transactions. Second problem was the high cost to store large data sets, because again, the volumes went up by orders of magnitude that you can collect. And then the third problem was to do with the applications. As I said, pretty much every enterprise today is starting to do machine learning and data science. And these systems were designed so the only interface to them is SQL. And it's awkward to, to take, all the latest ML algorithms published at NeurIPS and try to get them to run over that. So that's kind of the third problem. So because of this, there was this other kind of system design that became common to complement data warehouses, and that's called a data lake. So the idea here is, instead of trying to move things into a structured schema for historical analysis from the beginning, we're instead going to just have a low-cost storage system that can hold raw data in whatever format it arrives in. And that way we'll be able to store all the data we're getting in the enterprise at the lowest cost and then do something with it later. So these systems are usually based on a file API, so you can put any data format in there. And there are things like Amazon S3 or Hadoop file system, or all the other cloud storage systems. And the other factor of data lakes that became really important is that they were often based on open file formats like Apache Parquet. And these are accessible directly to a wide range of machine learning and data science engines and just common tools you might have for that. So for example, when I was a grad student working on Apache Spark, I was building a whole new engine, but I was, Spark was able to run on people's like petabytes of data from day one because the data was in open formats and I could just read them using these open libraries and do stuff with them. And the same thing is true with things like TensorFlow, PyTorch, Pandas, Apache Flink. All of these systems can use your existing data. So what this means is, as a data lake user, you get access to this very wide range of tools. And then, the data lake itself is not amazingly useful as a data management system, in that it doesn't have a lot of functionality. So for example, it doesn't have transactions, doesn't have really fine-grained security controls, and so on. So in practice, people will run these like big kind of analytics workloads on it directly for advanced things. But then for ad hoc analysis, they'll load a subset of the data into a traditional data warehouse, where you can do your traditional SQL stuff and maybe open it up to business users. So today, the vast majority of data in enterprises is in these data lakes. I would say at least 90%, maybe even more. Just as an example of this, it's hard to get the total amount of data in various systems, but I know like earlier last year, Snowflake, a data warehouse company that's like very successful, was saying they have 250 petabytes of data under management. And what we've seen, as I showed you, HSBC already, their data in all of their data lakes is 170 petabytes. And we have customers who have a single table that's more than 250 petabytes. So this is really where like the majority of enterprise data lands today. And making this data useful is one of our primary goals. Okay. So what are the problems? So I said, well, with data lakes, we solve the cost and the unstructured data problem. So are we done? Unfortunately, we're not. The problem with today's architecture, with these two tiers of data lake and then traditional data warehouse, is that it's a lot more complex. So basically, there are a few issues there. So first of all, your data reliability often suffers as a result of this problem. You've got these different storage systems, your data lake with things like Parquet, maybe engines like Spark running over it, and then your data warehouse, which has its own internal storage system and its own engine. And that means as you move data between them, you might get errors because maybe they slightly disagree on what a function means or how to store a particular data type and so on. And even if they perfectly agreed on that, you have all these extra ETL steps, basically jobs that have to run periodically to move data between them. And if anything goes wrong with that code, or if it's down, the end result for the user of the warehouse is that their data is wrong or is missing. So that causes a problem. Timeliness suffers for the same reason. You just have all these steps to get data into a usable form. And likewise, when you need a new data set as an analyst, you got to wait for someone to build up all these pipelines. So it really slows you down. And then, of course, you also get a higher cost because you're duplicating some of your data and you're paying for these compute jobs that just move it back and forth between systems and can even introduce errors. So these are, in practice, these are pretty significant problems. And like, these were some of the reasons that we saw a lot of customers asking us to make data lakes, more useful and to let them directly work with the data in there for more use cases. Okay. So what are Lakehouse systems then? So the idea then is to try to combine the best aspects of both categories of systems. So we want to implement data warehouse-like management and performance features, things like ACID transactions and indexes and so on, directly on top of directly accessible data in open formats. So if you're running a workload like TensorFlow that just needs to scan through a subset of the data, you can point it at some files and have it do that and have it understand the format because it's an industry standard. And if you're running, interactive SQL, or if you're doing transformations where you want to make a transaction or whatever, you can still do that. So that's kind of the goal. So if you are able to build this, it would look something like this. So basically, we still have our data lake storage layer, something like S3, but on top of that, we build a management and performance layer that implements features like security controls, transactions, all these kind of things you want, maybe caches and indexes. Basically, you then have two interfaces to this. You can talk to it through SQL using any existing tool that talks SQL, and you can also somehow get direct access to data files if you're running one of these large jobs with this huge ecosystem of engines that supports that. So that's the high level goal. Of course, the question is, can we still get state-of-the-art performance and governance features with this design? Because it's kind of, it's a little bit breaking, in some way, the concept of data independence, because we do want to expose access to these large, massive data sets to some of our clients, in a raw format, so we can work well on large workloads. Okay, so that's what I'm going to talk about next: how to build these, and in particular what we're doing. And we're not the only company trying to build this kind of thing. Actually, the internal data stacks at companies like Facebook and Netflix and so on arguably look like this already. There are also other startups and so on that are building Lakehouse platforms. Okay, so I think there are basically three key technologies or technical ideas that are enabling these systems to work well. And these have all come together in the past few years. The first one I'm going to call metadata layers on data lakes. So these implement that layer I was showing above that provides metadata management and implements these higher level data management features like transactions. And our example of that is Delta Lake, the open source project that we launched. Second one is engine designs. How do you build an engine that works well in this environment? I'll tell you about what we're doing. And then finally, for machine learning, you can get quite far by just connecting things like TensorFlow to your data, but you get even further if you start developing declarative I/O interfaces for these. And I'll tell you a little bit of what we're doing there. Okay, so let's start with the metadata layers. So the idea here is pretty simple. You have, your data lake is a collection of files basically, or objects in, in S3 or whatever in your object store. That interface isn't fantastic for data management because all you can do is like, get and put things using a key. So it's really hard to do higher level features. So instead, we're going to build this layer that sits in front of it and basically tracks which files are part of a table version or a dataset version in order to offer these richer management features. So what you have to do as a client application when you're accessing the data, instead of calling list on S3 and getting 1,000 objects back, you call one of these metadata layers. You ask it, hey, what are the latest files that are part of this table? And it gives you a list of those. And then you can then open the files themselves at high speed in parallel, the same way as if you're working with an existing data set in S3 and get all the benefits of this low cost, like highly performant and scalable storage. So Delta Lake is an example that we developed. Other companies are doing similar things. Apache Iceberg is a project that started out of Netflix and is used there. Hive has something called Hive Acid as well that does some of these things. So let me show you a little bit how they work and the surprisingly large range of features you can get out of this design. So let's first look at the problems with data management on a traditional data lake. So let's imagine we want to store a table of events and Amazon just gives us S3 and we can put in a bunch of files. So if that's all that our data is and it's sitting there, then that's a perfectly fine way to represent a table. People can just list this directory, read all the files and and go on and analyze it. But the problem is that we sometimes have to modify data and we want to do it transactionally. So for example, if there's a query that says, hey, delete all events about customer number 17, how can we do that? We'll have to, see where this customer is referenced and rewrite some of the files. So we might have to rewrite file 1 into file 1b.parquet, let's say, and then we have to delete file 1. We also have to rewrite file 3 and then delete that. So of course, all kinds of things can go wrong. Query could try to read the table while someone's doing the delete and see inconsistent data. So how does Delta Lake solve this? So in Delta Lake, as I said, we keep track of the list of files that form a particular version of the table. And we actually chose to do that within S3 itself. So one of the really cool properties of Delta Lake is it's as highly available as Amazon S3. There's no other service you depend on. And also you can use standard tools in S3, for example, to replicate it across regions and to back it up to cold storage and stuff like that. So basically, we automatically get kind of the same availability and all the features that Amazon builds into, into their flagship service. The way that Delta Lake does this is a simplified way, actually. There's basically a write-ahead log that we maintain in S3, where we have an entry for every version of the table, every transaction we're committing that's writing. And what I'm showing here is each entry in here actually tells you all the files that are part of that table version. In practice, it's not like that because it would be inefficient to commit if you had to maintain this list of potentially millions of files. So in practice, we have a log with deltas, in the project name, and we periodically take checkpoints and we come back to log and stuff like that. But logically, this is kind of what's happening. So now when you have a query like this one, you can go ahead, if you're doing the delete job, you can go ahead and rewrite some of these files, and it's fine because no one's going to see them until you commit a change into the log that says this is now the table. And so you can, the next thing you do is we want to atomically add this v3 object. There are different ways to do that with the different cloud storage systems, but it is possible to do it to make sure only one writer can add an object with this name. And if we succeed in adding this, then we know that we've committed, the third transaction here, and we know that readers who read v3 are going to see our new table. And so clients always read a consistent version. Actually, this even works with eventual consistency. Like even if the clients can't see these files yet, they know that they have to wait for them. So they get this. So we have a paper on this at BLDB 2020, if you want to check it out in detail. And the cool thing about this is you can also implement a wide range of management features over this. So you can implement time travel. If you keep the old files around for a while, it's easy to look at those. You can have zero copy clone by forking the log. So you can easily take your production data set, create a clone, and then test out a new pipeline without ruining the production one. You can easily see a history of what changed. And we've also added features to the format for a table that let you specify things like constraints. So as you write into it, we can enforce this. And there are also some other features that maybe a traditional data warehouse won't have, but that we found really helpful. One of them is actually treating a Delta table as a message bus, essentially. Think about something like Kafka. Again, it's possible, but it's difficult. It's operational work to run a separate system to maintain your message bus. So we found that a lot of people wanted to basically write into a table and have other jobs that listen to a table for changes in events. And so with Delta, you can do this because in the log, which data files are added and removed on each commit. So we actually have a Spark streaming source and Spark streaming sink for Delta that can listen to the events and just pick up the changes and treat your table as a stream. Obviously, this is with higher latency than something like Kafka because it does inherit the latency of S3, but for a lot of applications, it's pretty good if you have very large data sets. A few seconds latency works pretty well. And so the other thing that we recently added last year is support for secure sharing across organizations. So like, let's say you want to share part of your table with a different company, you don't want to give them access to your whole S3 bucket or anything like that. And you also want to be able to do transactions on the table and not have them see an incomplete result. So we have this open source protocol, Delta Sharing, where basically there's a server that a client can authenticate with. And if the client is allowed to read a table or even part of a table, if it's partitioned by some key, they get these short-lived signed URLs from S3 that allow them to read just those files. This is how people do file delivery over S3. So you can easily expose a snapshot to someone and do transactions and so on and make sure that they see things that are transactionally consistent. So these are, all these kind of features where like people had basically built a proprietary system that manages all your data. You can also do it on top of a collection of data lake files. And this is, I can't really understate how quickly this got adopted. We basically started giving this to customers around 2018, and it's already over half of our workload. We also open sourced it in 2019. It's basically, it was quickly adopted by enterprises because of the power of these management features like transactions, and it's also grown an ecosystem of commercial products that integrate with it. Okay. So that's kind of the first piece. So that's how we manage our storage. And there are a lot of open columns in there, by the way. I'm sure you probably see some, but designing these kind of layers is a very interesting problem. And as the industry is adopting them, I think people will also be open to new designs. Okay, second thing I want to talk about is the engine. What do we do to get great performance for SQL on top of this data lake? So the challenge here is, we want to use these open formats. You might be able to evolve them slowly over time, but it's not going to happen, every few days. So how can we get great performance when we don't have like full control of the file format? So it turns out, even if you've got these fixed formats, there are 4 optimizations that actually can get you pretty far in terms of performance. The first is having auxiliary data structures. We know the base data has to be in these formats, but we can have whatever data structure we want on the side. Then there's data layout optimizations, which affect total I/O, which is one of the main things that affects performance. And then there's caching, and there's just traditional execution optimizations. So the first 2, the goal here is to minimize I/Os for cold data by having these data structures and doing the layout smartly. And then the next 2 are about matching, custom engine performance on hot data. Okay. And so we are developing a query engine that does this, Delta engine that's basically our modified version of Apache Spark with quite a few modifications at this point. And there are also other folks doing similar things now. Okay, so auxiliary data structures, so pretty simple. Even if your base data is in Parquet, you can build all kinds of other data structures that speed up queries. And then also crucially, because of these metadata layers, you can maintain these transactionally too, in the same approach to make sure people see the latest version. So one of the things we support in Delta is min-max zone maps for data skipping. So for each data file, we know the min and max of each column. And actually Parquet already stores these in each file, but you have to open each file. It's a lot of seeks or IOs to do that, to see them. So we actually just take these and stash them, in a single file that we maintain transactionally with the Delta log. And so it's super quick to open this, look at the min max, and prune out over millions of files to figure out which ones you actually have to read. And of course, you can also do other things. We're also doing some work with Bloom filter indexes, and there's all kinds of other data structures you can try to maintain here. The second big optimization is data layout within the files. So even though you've got these fixed storage formats, you can definitely choose the order of the records you're going to put in there. And that has a huge impact on performance in the grand scheme of things. So for example, one of the things we do is multi-dimensional clustering with Z-order and other curves, other space filling curves. And this allows you to have, if you have your data set and it's in 1 million files, if you Z-order the data and then you query along any of those columns, you'll have a lot of locality and you'll have just a small subset of the files you have to read. So this made a big difference for our users. Third one is caching. Obviously, you can, once you load the data, you can transcode it into a different format. And so that's what we do on our worker nodes. We decompress the Parquet data partly, and basically we store it in a much more efficient format for later queries. And again, because we have Delta Lake, we can make the cache consistent as well, which is really nice. So as transactions happen, we know what to invalidate. And then the final one is vectorized execution. So we developed a new engine called Photon in C++ that's basically native implementation of many of Spark's physical operators. And this is what we're using now. And it outperforms these JVM-based engines by an order of magnitude in many cases. So it makes a big difference. So if you put all of these ideas together, you can get something that matches data warehouse performance on either hot or cold data. And just as some examples here, this is a TPC DS power test comparison with two data warehouses that I won't name. So our latest version is very competitive with those. In both wall clock time, it's also competitive in price. And we also recently submitted an entry to the actual official TPC-DS benchmark, which counts not just the power test, that's just like running queries one by one. It also counts concurrent query performance and load and merge performance. So as you update your data set, which is actually really important, probably takes even more time and money than interactive queries for most enterprises. So we also do really well end-to-end when we compare on these other metrics. Most people just run the power test, but the other things also matter. Okay, so that's kind of high level what we're doing. Now, there are also some unique challenges. It's not just like building a data warehouse engine, except now you read from S3. So here are some of the things we found to be tricky and interesting to work with. First of all, in this Lakehouse environment, as I said, the high level goal to help these users work with all the data in their company as quickly as possible is to reduce the number of transformation steps, loading that has to happen. So that means many users want to work on the raw data as soon as it lands from like that, that oil rig at Shell or whatever, that transaction at HSBC, they want to start querying it. And so that means you won't always have statistics, or they might not be up to date. So when we designed our optimizer, we have a cost-based optimizer, but we also added adaptive query execution, where we look at data at different points in the query plan, such as shuffle boundaries and Spark, and then replan based on what we see coming out of it. And that's really important for good performance out of the box, on many data sets. Another thing is that the data we'll get is often less processed, less curated, think about like processed foods type of processed. And so we also have to deal with kind of weirder data types that you might not really see in the hot path in a data warehouse. So for example, a lot of strings instead of IDs, lots of like JSON or semi-structured stuff. So we try to optimize the pathways for these to make them work well. And then a final one that's like interesting and kind of weird is people are putting this unstructured data in there. That's, as I said, large data sets, images, stuff like that. And so you often get records that are individually very large. And this is where a lot of engines that were designed for, business transaction data tip over. You can't have a record bigger than like a megabyte or whatever in them. So we actually design our engine and our memory manager to work well with these huge records so that you can actually work on all your data sets. We have a lot of kind of fun stories on like every dimension of a table that you think, someone could make large. There is a customer who did, right? There are lots of columns, lots of, like huge column names, huge records, all these things happen. So there's a bunch of stuff to like really make a system get great performance on data with the minimal processing in between. Okay, and then the final thing I'll mention here is declarative interfaces for data science and ML. So doing ML over a traditional warehouse is pretty hard for a couple of reasons. One of them is, unlike interactive, SQL queries for business analytics, ML jobs have a large results. They usually want to scan over a significant fraction of your data. So just sending that data into your ML engine over something like JDBC and ODBC is pretty slow. You have to transcode it. It might be served only by a single node that everything has to stream through. So it's really slow to work on large data sets. And so people will do a couple of things for ML. Some people export the data to a data lake, but then you have this additional step that introduces more staleness and quality problems. Or some people maintain a copy of the data set in both systems, which is, again, very painful to do. So with Lakehouse, first of all, we get the nice property that all of the ML engines already know how to read Parquet and these open formats. So all we have to do is give them a list of files, and then they go and read them. So that's pretty nice. And then they read them in parallel, and they don't slow down anything else. But we're also designing a bunch of declarative APIs. So for example, Spark data frames, if you're familiar with it, takes a data frame code in Python, but it compiles it to a query plan that runs on the same SQL engine and on Photon and so on, that we can then optimize. So we can use all the stuff I talked about to make it fast. And I also want to say that there's quite a bit more to make data integrated with machine learning and to design platforms that really do both. And we think this is an exciting area, and the CIDR community has done an excellent job of like doing research on these topics as well. So we see for our ML users, we see that integrating with data tools is really critical. And so we design our whole platform to make that possible. And we're trying to make sure that basically everything is data when you're working with machine learning. So just as an example, when you train models in production or for experiments, all of the metrics you collect about them become something you can query as a table using the MLflow open source project that we developed for that. So people love that ability to see them as data. We also built a feature store, and unlike most feature stores out there, we just say, hey, each table in our feature store is simply a Delta table. So you can always read it and join against it in ad hoc SQL if you want. And also each processing step, instead of being some custom DSL, is Spark or Spark streaming computations. So you can integrate not just ML feature engineering, but just data engineering in general. And likewise, of course, you can call the models and different things. So people find this a lot simpler than using separate products and trying to move data across them and all the friction introduced by that. So that's basically the kind of the Lakehouse part of my talk. So as you can see, these systems combine benefits of data warehouses and lakes. You get the open interfaces, which is really critical to run a huge ecosystem of software out there. No vendor can build all of that stuff by itself. You get rich management features, and you can also get performance and low cost. If your data is at rest, it's just the same cost as S3, which is very cheap. But the bigger thing is that they actually simplify data architecture. And so our users, like the reason they like something like this is mostly because of these factors: access, reliability, timeliness, that they can now work with more data faster and allow more users to do it. Okay, so I also want to talk a little bit about building a cloud platform, what's special about that, and then I have just a very quick thing on ongoing projects. So these will be much shorter. I just want to kind of give you a teaser on some of these things. So we built all this in the cloud from day one. We never had an on-premise software offering. And the cloud's a really interesting phenomenon that's basically taking over the software world. Most of enterprise computing is moving to the cloud. And it's because it fundamentally provides more things than just a bunch of bits on a CD-ROM that you install and manage yourself. Because the management is built into each service, that's already valuable. You don't need to do that work yourself, but also because of elasticity, being able to scale up and down and statistically multiplex resources. And just because of the velocity and cloud software, the provider can push updates anytime. You don't have to wait for like a 6-month or 1-year update cycle that each customer does on its own and maybe gets wrong and gets downtime because of that. So what I found is that if anything you're building, like let's say you're an amazing software developer, but your product is a bunch of bits, like software that people installed, even if it's open source and free, your main competition will be a cloud service that does the same task, maybe does it slightly worse, but is actually automatically managed. So it's really important to not just offer cloud servers, but actually try to do well along these dimensions that make cloud services often superior. So that's great, but of course building this is hard, and it's quite a bit harder than building the packaged bits. And there are many challenges. The first one is scalable operation. You need to operate the software for people. Okay, they were doing that themselves, so it's doable, and you need to do it at a scale way bigger than any individual user would have ever had to do, because you have thousands of customers, and it needs to be multi-tenant with security and performance isolation. So that's hard. Second thing is continuous releases. You want this velocity aspect of as soon as you make a feature improvement, people can immediately use it, and those on-prem users aren't going to get it for like a year or two. So you're years ahead of them in features. but actually releasing things quickly in a stable manner is quite hard. So you need to make sure that your process has no regressions and that it's very easy to fix any issues that come back. And then of course, elasticity, we found we had to redesign a lot of our engine to make it work well. So I'll just talk a little bit about some aspects of this. So one of the aspects I want to briefly highlight is developing control planes. So all the control services, like things that manage clusters, schedule jobs, do building stuff like that. We have a bunch of like independent services. And of course, they're developed by different teams and they can be released at different times. So the question is, how do you develop these systems so that the overall thing is reliable? And so, these are a few things that we found worked well to do that. And these actually tie a lot to the data management community. So the first thing is the state. We found it's obviously very important to reason about state in these services. We just use MySQL because we are fortunate that we can shard customers and customers don't really interface with each other's data. So that's nice. But we designed all our services to be basically stateless and to be able to quickly start up using a subset of the data in MySQL. And it made a huge difference over any attempts we had to keep state in the systems. Second one we found interesting is isolating components that scale differently or have different load. Like for example, the component that executes and monitors jobs should be different from the component where like you register a new job, so that even if the one that's scheduling is overloaded and backed up somehow, you can still set up a new job reliably and it will run eventually. Another big thing we found helpful is to make changes to feature flags. So our code always has, when we launch a feature, there's a fallback to doing things the old way. And there's a flag you can change, usually at the runtime, to switch between the two. It's never a good idea to just change the code and say, we'll have a migration and that's it. There are always reasons, you might have to go back. So we kind of learned this the hard way, and it's interesting to design. Watching key metrics. So we monitor our system, using Databricks itself. We get very, fine-grained data on what everything is doing. At the same time, we also found that, there are a few key metrics that often correlate and predict most outages. So just things like CPU load, database load, and thread pool exhaustion. If you watch those, you actually get pretty far. So it's an interesting takeaway for people, trying to use machine learning to do this and so on, is even if you just focus on these metrics, you'll get pretty far. And then of course, testing at all scales of the system. One of the cool things I want to mention, especially on the first one, is, these systems that manage workloads, like millions of jobs, thousands of customers, are very hard to build. And partly drawing on some of these ideas, I'm also involved in this research project, DBOS, that basically started when Mike Stonebreaker, myself, and a bunch of people chatted about this, and we're arguing actually to write all systems software in this way where the state is managed into a database. So we'll actually have a talk later today about this at this conference. Okay. And then the other thing I'll mention here is building elastic compute engines. So again, we found that you had to do this in all of the aspects of something like Spark. Spark was new, but it was initially designed for on-premise fixed size clusters. So we did everything from making sure you can add and remove nodes to a cluster at the granularity of one node at a time, to actually auto-scaling attached storage. So if your node is using SSDs, for example, we don't just plop in like a giant SSD and have the customer pay for it until they start caching data or writing out a lot of shuffled data. And then we request, network attached SSDs and add them one by one to make space. And of course, when things aren't in the cloud, all kinds of things are going to go wrong. And we designed our engine to be able to work with spot instances and to, basically give people the lowest cost to compute things. So we have to tolerate all these things going wrong in it. So this is showing one of the things we recently launched is what we call serverless SQL, where we actually maintain a big pool of nodes and give them to people for potentially just a few seconds or minutes at a time. And that introduces a whole new set of challenges. The traditional way we were doing before is everyone gets their own cluster, that in their own cloud account where, you just wait for it to start. But this is even farther along the elasticity kind of axis. And it's hard to make it both start quickly and give great performance. Okay, and I'll just briefly talk about some ongoing projects that we're doing. And then I'll have, I think, quite a bit of time for questions. So we think there's a lot more to do with data. We're not close to done. As I said at the beginning, enterprises are just starting to use large-scale data and just starting to use machine learning. So in the next 5 years, I'm pretty sure there'll be at least like 10, maybe 100 times more users working with these tools, with petabyte scale data sets, with machine learning, and there'll be orders of magnitude more applications using these. And of course, it's very exciting to figure out, what is the simplest way to help people build these and operate them and get a lot of users to actually work with all of the organization's data. So we're doing quite a few projects in, across this space. And again, our overall goal is to make it much simpler to work with, very large scale data with machine learning and to enable this next generation of users. We already have, given where Spark started and where it is now, there are easily 100 times more people who can use it today than who could use the initial, Scala version of Spark. So I'll just talk about a few projects: declarative data pipelines, Delta life tables, centralized governance, and also engine designs. So one of the things we're doing that's really interesting is we're taking declarativity, which is awesome, of course, for the compute that you do in each processing step, and trying to apply it to data pipelines in general. What do I mean by that? Well, when people run, processing jobs, they often run as part of a larger pipeline that's coordinated by a system like Apache Airflow. So you have SQL, each step your engine can optimize and can do cool things with, but then there's like this Python script outside that's sequencing the steps and running a bunch of them. So the question we asked is, what if we also had a data model of the pipeline itself, of all the SQL operations inside it, and also of the tables involved? Could we do interesting things by manipulating entire pipelines? So with Delta life tables, which is Michael Armbrust's kind of next project, he is the engineer who started Delta Lake and Spark SQL. So this is his next thing. The idea is the steps of your pipeline can all be SQL queries or Python data frame queries that you stitch together. And then his system can analyze your whole pipeline and do things like optimize work across the different tasks, fork the whole pipeline, so clone the tables and create a new copy of it so you can test a new version in development before you deploy it to production, hold it back, or even inject checks into the code, like modify the SQL to add tests that you write, in a logically independent kind of piece of code. So it's a very exciting thing to make it easier to build reliable pipelines end to end. You can see his blog post for more details about that. Second thing I want to highlight is actually the thing I'm working on there, which is Unity Catalog. So a way to have central governance for data and machine learning. Governance maybe sounds like kind of a boring word to people. It means access control, auditing, security, but it's actually, this is a very interesting time to work on it because the requirements are rapidly changing with new regulations like GDPR and just best practices. So people are very aware that, data needs to be protected, and they're looking for new system designs to do it at scale and to keep up with all the policies that are coming in. So we're designing a system that can do this across data and ML assets. One of the design challenges is how do you make it easy to express a wide range of policies, but still efficient to enforce them at runtime. But then, there's also, it's just a very interesting system because it collects lineage, audit info about everything, and then it lets you query it. So it's been a lot of fun developing this, and it's also very challenging from a design perspective. And then the final thing I'll mention is stuff we're doing in the engine. We're still doing quite a bit more with Photon, the native execution engine. We have a separate project Ether that's taking, like Photon is the physical operators, Ether is looking at the scheduler and the execution framework, pipelining between operators and so on. So basically rewriting even more of Spark to make it more efficient. And also in streaming, we just started a new team to revamp the streaming engine there. We see a lot of users using streaming. We made it very easy to use because you can just take any SQL query and turn it into a streaming query. And we see a very fast growth of it. So we wanna make it even better. So that's an overview of what we're doing. So just to conclude, again, I think Databricks was able to go to this stage because it really tackles one of the core problems organizations have, which is actually how do I just get people access to data and let these diverse users seamlessly collaborate. If you can't do that, then it doesn't matter how fast your platform is, what cool features it has, what cool consistency model, because they don't have their data in it. And this is a core problem with working with data. Any steps you add, any delays will make the experience worse for downstream users. So it's a really interesting one to tackle. And there's a lot left to do in this space. We're hiring, if you're interested, and we're definitely excited to chat about all these things. So thanks, and happy to take questions.